Our electricity network is undergoing the biggest expansion in nearly 50 years. Old and polluted power stations are closing, and new, cleaner energy is on the way. National Grid is at the heart of that change, providing the networks that connect us to the energy we use.
National Grid has a huge job ahead of connecting up new sources of energy, renewables and other low-carbon forms. We felt that this was the time for a new approach.
We're not kidding ourselves. We're not expecting people to love pylons, but given the fairly significant expansion that we've got to make in the network to connect up this new generation over coming years, we've listened to what people have said and concluded that we needed to look at trying to find an alternative design of pylon to go alongside the more traditional lattice design. The development of a new pylon design has been a really exciting challenge for us here in the UK. Now, a new design has never been intended to replace all of the existing lattice pylons that we've got around the country. But what it does do is it gives an alternative option where we need to build new overhead lines to connect up this new generation.
The process started with National Grid working alongside the UK Government and the Royal Institute of British Architects to launch an international competition to find a new design. From the 6 shortlisted designs, there was one unanimous winner. Rasmus Hennings and his team at Danish architect firm Bystrup came up with a winning design. Early on in the process, they had realised technology from other industries could help deliver a pylon much smaller in size than the traditional lattice tower.
Looking at the English landscape, we felt that it was important to make a small compact tower that would reduce the visual impact. Here the starting point was actually the triangular configuration of the conductors. And the main idea here was doing a diamond-shaped insulator unit, and by doing that we could make this tower much smaller than the traditional lattice.
The first thing that strikes you is that all the wires are held from one attachment point, and this is just unheard of. What you normally have is 3 separate arms on structure to hold the different wires, but now everything is held on one attachment point. So we've looked at that particular connection point and said, okay, how do we ensure it's robust enough?
It was the first time that a circular monopile structure was being considered for high voltage power lines in the UK. So over the months that followed, National Grid engineers set to work with their Danish partners to build 2 prototypes of T-pylon from what previously had just been paper designs. Could a T-pylon actually work in reality?
Each arm has to carry 60 tons. That's around, let's say, 30 normal cars hanging in each arm. That's an extreme loading event. So we are assembling these rolled circular tubes using a so-called slip joint, which is quite a novel approach.
The slip joint test demonstrated to us that the connection was sufficiently strong to minimize deflection and minimize the risk of it actually turning.
The suspension pylon was the first prototype to be tested, and it would need to be capable of carrying power lines in straight lines over great distances, with enormous pressures placed on its 2 diamond-earring structures. The second prototype tested is the tension T-pylon. The tension would be used when the span needs to turn corners or bend around the landscape. The central frame is the major visual difference here, needing to be capable of taking the tension from over 50 tons of wires as they try to bend the pylon to resist the turn.
National Grid was looking for a modern 21st century pylon design that would meet the aesthetic requirements, bring an innovative design concept that could be made a reality. And in the T-pylon, we think we found that.
So a conventional pylon has hundreds of parts. It's basically like a large Meccano set, and it all bolts together on site. It takes quite a bit of time. The T-pylon consists of only 10 structural components plus the bolts. So it's very simple to bolt together.
From design, through testing, to reality, National Grid has established a full family of T-pylons capable of transmitting electricity through even the most challenging of landscapes.
We needed a family of T-pylons because they all perform different functions. Sometimes they need to go straight, sometimes they need to turn a corner, and other times the line needs to end. The most common type of pylon is the suspension pylon, and that's used where the lines just carry on in a straight line from pylon to pylon. The second type is a flying angle pylon, and that's just used for small angles of up to 10 degrees. The third type is a tension pylon, and that's used for larger angles up to 30 degrees. Those three pylons combined are able to be joined up by the wires or conductors to stretch out over the complete route. At the end of the route, we need the fourth type of pylon, which is a terminal structure, and that's for ending the line. And those terminal structures are also used if there's a transition where we move to an underground cable. So for the family of pylons that we've developed, we're looking at a variety of options, different surface finishes that will best suit the environment that the T-pylons will be installed in.
Bringing this family to life in almost 1 year is quite a magnificent task, and it's only due to National Grid's huge engagement in this and our very good cooperation. So I think we should all be very happy. It looks very elegant, light, and so we're very happy with the design.
I'm really looking forward to see a whole series of towers being strung, see how it looks in the English landscape.
Bystrip have gone forward with us and put this structure together. We're ecstatic, we're overjoyed.
The T-pylon gives us a fresh new option for our major transmission projects ahead. I think it will be welcomed for its design features, and happily it will also do a great job from the engineering perspectives to allow us to keep people's electricity flowing safely.
From landscape architects to 3D modelling to testing the prototype models, National Grid's journey to find a new pylon fit for 21st century Britain has come a long way. Technically, most of the work has been done. They've proven that the design can work in reality and can now provide an accurate account of how the T-pylon will fit into the landscape.
It's been a massive achievement to take this from concept through to something that we can actually build and use in the space of just 2 years. It's going to be really interesting to see what people think.